Professor is good. Can we start?
Yeah, okay.
Thank you. Thank you. Good evening from Explore the Space to the participants from India, and good morning to participants from USA. We also have participants from other countries, particularly Uganda, Africa, and UAE. Welcome to all of you. We welcome you to the first edition of the webinar series, Making Space Exploration Safe and Sustainable. Space technology and exploration is driven by multidisciplinary approach, and it provides opportunities for students in all disciplines of science and engineering. That's exactly the message that we want to convey. From one satellite in 1957, Russia's Sputnik, today we have over 9,000 satellites in our orbit. Satellites that were big and bulky have come to be the size of a loaf of bread, doing faster and greater work. And the Indian space exploration story that has been exclusively driven by ISRO, an inspiring organization, is seeing great winds of change as the space sector in India is being privatized.
Venkat, we can't hear you.
You can't hear me at all?
I can hear you, DV. I can hear you, but maybe not everybody.
Tim, Dr. Manisha, am I audible?
I can hear you. I hear you. I hear you fine.
Yes, sir.
Thank you. Thank you.
Yeah, me
Thank
too.
you, ma'am. Thank you. Thank you. Thank you. Friends, today we are at a situation where we need to emphasize and work towards making space exploration safe and sustainable. As I talk, as I mention this, one cannot help but then think of Madam Sunita Williams. We all wish that Sunita Williams, along with a friend, safely come back to Earth very soon. This webinar series is powered by Anant Technologies, a leader in the Indian space industry, and we have a special address from Dr. Subbarao Pavluri, a powerful change maker in the Indian space spectrum. Dr. Subbarao is a technologist and an entrepreneur with extensive experience in Indian space program for over 4 decades. The inaugural address of the webinar is to be given by Dr. L.K. Sharma, former president of Indian Ceramic Society and a very big name in the world of ceramics. Mr. Tim Dyer, who is to make the keynote address, has been a great supporter of our space education outreach efforts, is currently the executive director of Fralock USA, a leading company providing precision engineering solutions for aerospace, medical, and semiconductor industry. Dr. Manisha Vidyavathy, head of the department Ceramic Engineering, Anna University, to give the special address on career opportunities in ceramic industry. For the students, the message is this: Explore the Space provides excellent platform for learning and networking to all those who want to pursue space and allied industry as their career. I'm sure we all know the importance of networking for a successful career. With this, let us move to the main program, and I request my colleague Khader to play the special address that's a recorded speech from Dr. Subbarao Pavluri. Thank you, ladies and gentlemen.
Namaskar. Greetings to ladies and gentlemen, space enthusiasts, space entrepreneurs, and my dear students. From different geographies who are participating in the first edition of the webinar series. Name of the title of this is Making Space Exploration Safe and Sustainable. This is being organized by the ISRO-registered NGO, Explore the Space. As the chairman and the managing director of Anant Technologies, a premier satellite company that is into design, development, and fabrication of highly reliable systems and subsystems for the global space markets, I am delighted to have this opportunity to make my initial remarks and support this initiative. The inaugural address of the seminar will be given by Dr. L.K. Sharma, CEO, Mahanama Ceramic Development Organization, and is also chairman India chapter American Ceramics Society and former chairman Indian Ceramics Society. The special address will be given by Dr. Manisha Vidyavathy, head of the Department of Ceramic Technology, Anna University, Chennai. Mr. Dyer, Executive Director and Product Management, Fralock, USA, will be making the keynote address, and the theme address will be presented by Dr. D.V. Venkatagiri, CEO of the Explore the Science, Explore the Space. That is very impressive lineup, which includes a top-class technology institution in India, Anna University, very famous university. Scientist who was the president of the Indian Ceramic Society, the keynote address speaker from the USA, a country with which India is making rapid forward march in space cooperation and to explore the space, an NGO that is connecting all of them, very connecting all of them and promoting space education across geographies. This is very notable. On today's topic, making space exploration safe and sustainable. My dear friends, this is a high time that we need to really get our act together to make our pursuit of space sustainable and safe. From the first satellite Sputnik, which was launched in 1957, today in 2024, we are in a situation where we have 9,500 plus satellites orbiting Earth, and this number is growing very rapidly in leaps and bounds. So the message is very clear that space is getting crowded. Some of the most important challenges that I see in making space exploration safe and sustainable are: number one, space debris; two, need for advanced materials for space exploration; and three, very limited cooperation now among the countries in space exploration. I see these three are the major challenges right now. Space debris are human-made objects, as you all know, in space that are no longer useful and can be hazardous to spacecraft. This includes old satellites, rocket stages, instrument covers, separation bolts, and fragments from the various collisions and explorations that happens in space. To make space exploration safe and sustainable, we must prioritize technological advancements that reduce the environmental impact, protect the astronauts, and minimize risks associated with the spacecrafts and with the debris. With the space debris is the major threat today. It is important and interesting to note that much of the research that is happening on space exploration is related to materials that can be used for space exploration. Latest developments in materials, including ceramics, play an important role in the running to the future space missions. International collaboration in space is a strategy that involves countries working together to share costs, access to each other's resources, and achieve common goals. We need to take steps to promote greater global collaboration on various policies that address resources sharing, environmental protection, and safe deorbiting procedures that will further support the sustainable growth. That's for space exploration, fostering safer and long-term human presence in space. The International Space Station is a shining example for the global space cooperation. I urge the participants of this webinar and others who are going to see the recorded version now to take active interest and pursue space exploration and play an active role in making safe and sustainable space for all of us. Good luck to all. Jai Hind. Thank you. Namaskar.
That was a very good recorded speech that we had from Dr. Subbarao Pavluri. Thank you, ladies and gentlemen, for your patience. We are fortunate that we got this speech day before yesterday, and we intend to play this speech of Dr. Subbarao as we run different versions of this webinar series. Now, I take pleasure in inviting Dr. Lalit Kumar Sharma, Dr. L.K. Sharma ji, formerly Chief Scientist of Central Glass and Ceramic Research Institute, former President of Indian Ceramic Society, Chairman India Chapter of American Ceramic Society, and the CEO of Mahanama Ceramic Development Organization for his inaugural address. Dr. Sharma ji, please.
Yeah. Can you hear me? Yeah. Thanks,
Yes.
Venkat. Thanks, Venkat. Dear friend means Tim, Subhash, Manisha, Venkat and team and other participants here. Good evening for all the people and good morning to Tim and Subhash. Once
Good morning.
again, okay?
Yep.
Yeah.
Good morning.
Good morning. Good morning. Yeah. What explore the space every time the name says that explore the space mission is still far, far away for all of us. We have still a lot to do. And when we were studying, we were taught that the journey of ceramics started through pottery, made 20,000 plus years back. And today we reached to aerospace ceramics. And we are discussing aerospace ceramics, advanced ceramics, all that. And we remember that someone who has done this first fire brick that was made around maybe around 7,000 BC before Christ. Then firing of fired brick was made around 4,000 BC. And then we came to the Tower of Babylon. That was 2300 BC. And nowadays, time is for advanced ceramics, what we can say aerospace ceramics, which has a lot of things. Ceramic coatings are there for space vehicles, and we are still doing a lot of research in this field. And ceramic seals and so many ceramic parts are there for the uh, engine and purpose is that simple purpose is wear resistant and this ceramic parts which has you can say in micron polishing gives that self lubrication effect. Non-silicate glasses also are important and lot of scope is there for that. So means now maybe in Tim and Subhas, maybe for you people that the department where I studied ceramic engineering it was in 1924 and it is 2024 that IIT Banaras and maybe Subhas may know that Dr. Mrityunjay Singh in
Yes. I know.
aerospace he also studied there. So our department is celebrating this 2024 as the centenary celebration. And I have written almost 15 pages on advanced ceramics and that will be published. So I'll, when I visit to this Daytona Beach conference, I'll bring you the copies
Please,
to
yeah.
both of you.
I
Yeah.
look forward to it. Yeah, yeah.
So I am not going into the details. And today only Mrityunjay Singh has landed in Delhi and he
Oh,
has
wow.
gone to Varanasi.
I see.
And he will be the chief guest at IIT Madras Indian Ceramic Society annual session. He is the chief guest. So ultimately to the participants, they are from most of the big universities in India, IITs. They are there, and I am not going to into the details. So ultimately, I want to convey that it has lot of applications. It is a this aerospace ceramics, advanced ceramics is a emerging field. Lot of in IIT Madras also, lot of students after doing PhD have entered into startups. Lot of scope is there for collaborations. Now, my friend Tim, as usual, always has inspired us and the participants several times in the past in big way. So, I think he will do same thing today also. Manisha will talk opportunities in this field. I once again welcome both of them on virtual stage and look forward for the great outcome. And Venkat, you and your team really is doing a great job bringing all these students, teachers, professors from different institutions to this virtual stage, means this webinar. So congratulations to you and your team to bring big gathering together.
Thank you,
And
sir.
I would like to tell that Subhas, this Manisha is getting a international award of American Ceramic Society in Daytona, and she will be
Yeah,
the first lady. She is
wonderful.
going to be the first lady from India.
Great.
So first,
Congratulations,
yeah,
sir.
yeah.
Congratulations.
So
Congratulations.
your lecture and all this will see that time, and definitely will meet you. So let us listen to Tim and Manisha. Thank you all. Thank you very much, all the participants. Thank you.
Thank you.
Thank you. Bye. Bye.
Thank you.
Yeah.
Thank you very much, Dr. L.K. Sharma ji, for your inspiring words. Thank you very much. We look forward to continuously working with you in our journey of space education. Ladies and gentlemen, I have pleasure in introducing a great friend of Explore the Space, Mr. Tim Dyer. Tim has both a bachelor's and master's degree in material science and engineering from the University of California, Davis. He was the president of Elcon Precision in San Jose, California, before moving to become the executive director of Fralock, USA. Tim has over 3 decades of experience in technical ceramics, refractory metals, and semiconductor. Over to you, Tim. Thank
Thank you, DV, and I feel it's what an honorable group of folks to be here. Just to be transparent, Subhash was my thesis advisor for my master's thesis at UC Davis. That was in I think 1993. I think, to let you know, just to wind back the clock. Yeah, it's a long time ago, and so I do appreciate him being around. And let me see if I can share my screen here to get the right screen here. These things down. All right, and just to let folks know, I started out not as a ceramist, I'm a material scientist, and so when I started my initial work, it was just it was my first job out of school. When I went to applied materials, they gave me the ceramics projects, and I've been doing ceramic work for my entire career as a result of that one first project I did at applied materials. Making semiconductor devices, chips. So it was really just a kind of a neat opportunity. So anyway, I currently work for Fralock, and this talks about a little bit about the history of ceramics, and it's also about ceramics and how it enables our lives, like with technology, and then it goes into reliable space systems for propulsion. But there are so many aspects of the space, it's really hard to do this in one seminar. So that's why we hope people will come and attend a series of seminars, or even look at the space course that Explore the Space offers, as a way of kind of supplementing your education, because definitely the interaction that we have in these webinars, you can't get from a course online. So you need to do both to get really the best benefit of the program. Okay, so it's just a little bit my agenda, a little bit of the company, and then some history, which Dr. Sharma talked about, but I have a little more details on that. But ceramics is great, some of that. And then about Silicon Valley, because I'm located in California and I work out of Silicon Valley and also out of San Diego. My 2 factories are there. And so you understand a little bit about the culture of ceramics in the United States, especially in California, but also how it's a part of a large, I guess, mosaic of ceramic technologies that are kind of scattered about the globe. It is a global industry, a global collaboration, a global community. Okay, a little about Fralock. Fralock is a material science company that provides solutions for a lot of high-tech space and medical industries that are on thermal control. So I'm responsible for engineering for the Engineered Technical Ceramics division. We have 160 people in California, but most of our solutions are focused on temperature control of devices, and that's our niche in terms of materials technology. It's a pretty good sized company of 700 people overall, and we're ISO 9000, AS 9100D. We also have medical ISO 13485 for medical systems. We make a lot of laminated polymer films and a lot of ceramic components, a lot of flexible circuits that can be used in extreme conditions like vacuum, radiation, space, or could be high temperature. Yeah, and then to kind of Dr. Sharma talked about this, but this is my take on the history of ceramics. I presented this to American Ceramic Society students in 2021, but this is a shortened version of it, 28,000 BC to 2024 AD. Historically, we define human progress by key materials, and people see this, you know, like the Bronze Age, the Iron Age. People don't really talk about the ceramics age because it's been around for almost 30,000 years. And so ceramics, why ceramics been around so far is they really require basic ingredients that everybody has. You don't have to mine these things. It's easy to find. The ancient Greeks defined these 4 basic elements, because they didn't have the periodic table, as earth, water, air, and fire. So combinations of earth, water, fire, and air can create materials that can make your life better, like store water, artwork. You can make tablets. You can make like a roof for your home. You can make a floor, you can make a road. All of these things are just from these basic elements. So that's why ceramics have been around for a long time. Ceramics are made of these elements. Now, in the modern days, we still use these Greek elements, but we have very, I guess, fine and purified and optimized processes from the last 28,000 years. We have electricity now helps us with gas firing for heating things. It can be done within our gas. We have firing atmosphere control, so we create nitrides and borides and carbides, in addition to oxides, which didn't, you know, in the beginning, you couldn't make really any carbide or boride materials. You didn't have the technology. We actually are really good in Earth at finding now the correct ingredients. So we have refining process and purification processes that are part of the greater ceramics industry, like Alteo or Almatis, or it could be Bukowski companies that are really refining these materials to give us great ingredients. And then honestly, water is not always the best thing, like with aluminum nitride or some materials that react with water. You could use solvents to make ceramics out of non-oxide materials. And so organic binder systems, organic milling processes really enable that. So all this stuff comes together. And to kind of get the idea of history is like, we look at history of ceramics, it's been around a long time. Like I'm in North America. When India was developing ceramics and creating art and pottery, the United States was just a vast wilderness. There was nothing here. So in terms of the countries that have a significant impact on the ceramic industry, it's really the Middle East and India that have the largest impact, because you've had large populations there for thousands of years. And even Greeks and Romans relied on pottery for expression of art or food storage. That's all been done for so many centuries. So understand that it's very honorable to be speaking to a group from a region in the world that actually has such great history with ceramics. As you see from the list here, it started with artwork and then pottery, winemaking, 7,000 BC. I think the first beer was like in 4,000 BC or something. Again, all kind of enabled by having pottery. You have beads and glassware, so you can have jewelry and artistic improvements for decorating yourself, which is 5,500 BC. A lot of improvements by improving the ceramic itself by making porcelain, 600 AD. And then more recently, metal processing, melting, so you can make, you know, like steels and stuff. So if it wasn't for ceramics, you wouldn't have a Bronze Age and you wouldn't have an Iron Age. I mean, that's the kind of part that the history of ceramics. And then all these other processes, including most recent developments in France, the Dyer process for creating aluminum oxide powders, really a simple process that takes aluminum metal and creates aluminum oxide hydrate that can be processed into aluminum oxide to make advanced aluminum ceramics. It's kind of some summary of more modern applications. We have capacitors that are this within the 20th century. So now you're kind of within the last 100 years. You have high voltage materials, transparent, durable materials, nitrides, carbides, zirconium materials, which that comes out of Australia, a lot of mining out of zircon sands that create really awesome ceramics for fuel applications or high temperature for like exhaust systems. High temperature superconductors, which you've seen and they're getting better every day in terms of their ability to operate up to maybe minus 70 or minus 80 C. Low fusing ceramics, 3D printing, which is now becoming a big deal. I think it has a ways to go, but again, we can always talk about that in future seminars. And I do know folks that are working on 3D printing, especially for in space, because you can't take all the parts with you when you go to space. If you're outside in the atmosphere and you want to make a replacement part, you're going to need some sort of 3D printing capability. So that'll be done in space. So 3D printing becomes key for it really, or on the moon, you're going to have to make something out of the aluminum on the moon. You'll need a 3D printer. Solid state electrolytes, all the battery stuff that you have, the fancy, your cars, your drones, your electric bike, all of this stuff is really enabled by the lithium-ion batteries. It's another type of ceramic material as the cathode itself. And then most recently, real big for Fralock is these artificial intelligence microchips for advanced computing. They require a lot of silicon carbide. And we see this growing dramatically, the use of this material, the carbides, because of its dimensional stability and basically ability to resist really high temperatures. I think it's around 2,500 centigrade or something, its limit, which is pretty amazing. So all of this, the better the kilns are, the better the ability to fire things. We have more and more materials. So ceramics is really has evolved a lot in the last 100 years. Now, a little thing about Silicon Valley. Silicon Valley is a great mix of technologies, and it's a great community. We have the car people, the electric car people, we have the biotechnology people, we have X-ray people, we have semiconductor, Intel, AMD, chip makers, you have applied materials, Lam. So this community creates a variety of products. And so the next slides talk about some of the products that come from Silicon Valley or California in general, close by, and how they influence us as a society. So the first theme is ceramics are really helping us improve our health and quality of life. So these are pictures that are products that are involved with that are kind of from locally from the area. There's systems for cancer treatment. There's systems for taking the salt out of water to create drinking water from seawater at low energy. There's diagnostic healthcare devices like for finding cancer in your body, artificial joints and bones. Fire-resistant materials. In the lower right-hand corner here, these are for wine fabrication. A friend of mine makes these in Napa they're concrete cylinders for aging wine. Very, very neat. There's materials that can clean the air. There's dentistry components like artificial teeth made out of zirconia, and also products related to the manufacturing of coffee or tea. And UC Davis does have a coffee program in its chemical engineering department, which is also kind of relies on some of this technology. In terms of communication, there's a lot of products in the communication sector. Your cell phones and batteries and computer screens, especially the flexible computer screens, high density batteries like made by Enovix or Amprius now use silicon anodes or Sila Nano that could really have high energy density. That's kind of from the area. There's lasers that are involved in the area. Again, sensors for safety like accelerometers or LiDAR sensors for your car so it can communicate and navigate on its own. You got a lot of cell phone communications, components used in microsatellites, and then again, 3D printed structures that can be done to make active 3D circuits. So AI chips, artificial intelligence chips, are often multiple circuits that are assembled in stacks to create three-dimensional networks. So in addition to the microstructure of chip, you actually have multiple chips bonded. So that's all these 3D. So to make chips that kind of act like human thought, they have to almost simulate the 3D nature of the human brain a little bit in structure so they have good communications. Here's a little on security in space. This is kind of, I guess, core to this group. There's a lot of ceramics used in it. A lot of it, most of it's in propulsion systems. A lot of it's in guidance systems. There's also some I'd say some cursory like looking at cargo inspection systems using large X-ray machines, and also guidance systems for autonomous vehicles. really, when it comes to going into outer space and deep space, it's going to be difficult to find someone who will volunteer for a mission where they fly to the end of the solar system. So it'll probably be an autonomous vehicle that will do that, which will have to have some thinking capabilities and some sensors installed in it. And again, ceramics can really enable that. Vacuum tubes, high thermal conductivity circuits, a lot of stuff is, ceramic tiles for reentry, so you could shield your heat for yourself from heat. There's also things that could protect the police officers in your town, like bulletproof glass, or it could be armor plates that protect them from debris, or even protect you in your vehicle. If you have an accident, there could be protective surfaces in there that again help protect your body by the right material put in the right location in the design. So great stuff that comes through. And then again, hypersonics. Dr. Scotty McCormick from UC Davis is working a lot with hypersonic materials and borides. He does some really great stuff. His parts are so hot, he can't even have a crucible. He has to levitate them on jets of argon gas just so that they'll burn up his system. So he's running around 3,000 centigrade. Again, really great stuff with hypersonics. I really see that as important to the future ceramics. Last theme is energy. Ceramics have involved a lot. The solar panels are silicon, and they're all over now. And I heard just recently that it was Portugal had 5 days of operation without using only renewable energy, just using solar and wind. Amazing. We've come so far where we can really wean ourselves from using fossil fuels. These rare earth magnets that are used in a lot of car motors and stuff are awesome. We have those. Thermal energy, there's a lot of companies involved with that. I have friends working with thermal energy where you take heat from an exhaust system of a large factory and you store it in ceramic plates, and then this could be recovered. It's Rondo energy. Non-flammable separators for batteries. We all know lithium-ion batteries can set on fire. By putting aluminum oxide in a separator, you can prevent this fire. And so that's another way of making it safer. There's also ceramics that convert hydrogen and natural gas into electricity. So realistically, it's amazing. You could take at high temperature, Bloom Energy does this, a source of hydrogen gas and generate electricity. So it's another way of creating energy, and it uses really ceramic materials. Safe home energy storage systems like Tesla Powerwalls. They're pretty expensive, but like my house here, I have an energy storage system that backs up my internet, and I also have Starlink satellite for all my communication, which uses satellites, and that's also backed up with batteries. So I basically don't have to worry about if there's a power outage. I could definitely keep communicating. Again, all related to ceramics and space. Emerging materials is to keep your eye in terms of going to school on where the industry is going. What is becoming important? Hydrogen energy, lithium-ion batteries for energy storage, fusion energy. They like Commonwealth fusion. The future is that we need to look at these things. We have to balance cleaning up the environment, improving healthcare, and being more efficient with energy. That's as ceramists. Long-range transportation would be standard in 10 years. So if you have electric bikes or electric moped, could be electric car, these will become standard. I think gasoline vehicles would be kind of a neat thing to see in the future, like something in a museum. And that could maybe only be 10 or 15 years away that we're at that point, and that cleans up the atmosphere. So energy materials are really, really more and more important. So just keep that in mind. These are kind of sulfate and phosphate materials and batteries. Alumina, silica, lithium oxide, silicon anodes allow us to store up to 3 times the energy in a normal battery than we used to, which is great. Hydrogen electrolyzers help create hydrogen gas or even electricity from hydrogen. And then nuclear energy is not dead, everybody. It's still around. And if you're going to launch a spaceship that's going to go to the outer reaches of our solar system, the solar panels won't work. You have to have a source of energy, and nuclear power is that. So nuclear power has its role. And then fusion energy is a future thing, and I hope it happens, but we can't, again, that's by collaborating as a mixture of different disciplines, we can make that happen. Okay, a little bit now on materials solutions for space applications. Flexible materials and ceramics, these are really focused on reliability. In space, there's no tow truck. You can't call AAA or you can't call your local automobile society to have them pick you up. You have to have things that work. So a lot of work in space materials is de-risking. At what risk factor do you determine you want to leave on your trip? I have an 80% chance of making it. That probably makes sense. If you have a 30% chance on making it, you don't want to go. So the idea of space technology is to have enough data and enough confidence in your designs that you feel you could make the trip and come back or meet your objective. Because in addition, like with NASA DART mission, when we built the engine at Elcon for the DART collider, you know, we knew that we only had one shot at it. So of all the people involved in the project, there are probably over 1,000 people and engineers involved in that project. And it would just take one person's mistake to make the project worth nothing for everybody. So the pressure was intense that we had to make sure that our solution worked for DART, that the thing, when we demonstrated that we could collide, the double asteroid redirect test, that we could collide with a meteor and displace it, we only had one shot at it. It's not like the thing could turn around at 180,000 miles an hour and make the target. So again, these systems have to be reliable. So first of all, I kind of present this and about is we have the common propulsion system. So most people are aware of like SpaceX and their large launch systems, and I call them launch systems because they lift the payload from space to Earth. So they're typically large and they have tremendous thrust values, and you can see one on the right-hand side. And then on the left-hand side, you see this solar electric ion engine on the NASA Dawn spacecraft and you see the blue flames there. The blue flames are the propulsion system. So then it's basically, you know, why do these craft look so different? So, you know, people in general would kind of see spaceships as being these rocket-like looking things, when realistically most of the stuff that's in space is more boxy or cylindrical in shape, and it's using a different type of propulsion system. So understand that first is the less common application is this payload system. It may have thousands of these smaller satellites inside it, and if you've ever seen a Starlink deployment, if you're out looking in the sky, you see that they may drop 4,000 satellites out of, or 3,000 satellites out of one launch. So most of the stuff in space looks like this guy on the left. Now, different near orbit versus launch propulsion systems. And I put questions here that perhaps at the end we could discuss if you want to talk about them, just to make you think about the thought process of why these are so different. These large systems they're lightweight and they're powerful. They use tremendous amounts of energy to lift things into space. That's sort of why in the future it'd be better that we could make things in space so we don't have to waste all the energy lifting them up there. That's a huge environmental, I'd say, pay or cost is that system. You know, aerodynamic in shape because they have to fly through the atmosphere. They have to withstand high temperatures. The advantage of space is there's no wind to displace. There's no air to displace. So you don't need to be aerodynamic. These microsatellites.
Can I have a minute, please?
Sure.
Tim, this is a special announcement to the students who are part of this webinar. Mr. Tim Dyer will be posing questions like this. The question in this slide is, which spacecraft travels faster? How small can microsatellites be? You are most welcome to send your answers either during the program or after the program, and the right answers will receive a special gift from Explore the Space. This is a very kind and brilliant idea that we had from Mr. Tim Dyer. Thank you, Tim, for this. And students, we appeal to you to make the best use of this. Thank you, Tim.
Yeah, and I think, and also just put them in it's better if you just put them in the chats, and then DV can look over the chats too after the talk. And then we can always, if you want to provide more detail, we'd like to hear from you in general. The whole idea of these events is to have more interaction with this events. You can take the class that's offered, but again, you know, this is a great time to talk to an expert. So I put these red questions in here to get you thinking. That if you want to answer these questions, and also it helps you focus on the talk. So right now, microsatellites, you know, they just need enough speed to stay in orbit. So they're limited. They don't have to be flying like a lot of them don't have to fly out in deep space. They have to be power efficient, and think about that. It is expensive to launch a satellite. They have to be up and reliable. A lot of them use solar winds or solar power for energy. That's a sustainable source of energy for devices to be reliably powered. And then, example here is a low ion power engine. So again, do these really have to be big? The microsatellites, nanosatellites, do they have to be big? And also, which one do you think is faster, the launch system or the microsatellite? Okay. A little bit about satellites in Earth's orbit. There's a few places that you could launch satellites, and I have identified on this diagram like the Hubble, Iridium, and the International Space Station. And what you kind of see is that they're actually pretty close to the Earth. They're within the inner Allen belt or the Van belt. So the Van Allen belt, you can kind of see here. The actual numbers here are the speeds that are required to maintain a stable orbit. So far out in the orbit, to go around Earth, you have to go, of course, faster. In the center, you're a little slower, but this gives you an idea. GPS satellites are actually located quite far from the Earth. But if you want to take pictures or photos of the Earth, it's good to be close to the Earth in terms of, so you have less atmospheric effects. But you can see from this diagram that there's a variety of locations that are heights from the Earth. And then there's stuff that are way out in the outside that we call this geostationary Earth orbit. Doctor, again, this is a lot of debris out here. So this is sort of the warning that, especially since people are putting a lot of satellites near the Earth itself, there is some debris field. So we really have to be conscious about space debris and how they can interact with our crafts. It is definitely better to launch something farther out. There'll be less popular orbits with less debris, but we are creating sort of a problem. We have a lot of satellites kind of close to the Earth. Electronic propulsion systems are primary out there. They're ion engines that move these things around. They use dielectric ceramics to hold off the high voltage and also to create electrons to interact with the materials within the engine. I'll show you that next, how that works. And then they run from altitudes of 90 kilometers to 30,000 kilometers, speeds 11,000 to 30,000 kilometers per hour. Generally kind of see that there's this lot of this spacecraft that are close to our Earth, and they're used for communication and have a big impact on us on a daily basis. Ion engines are the primary way of these things flying. So it's interesting, if you have a heavy atom like xenon that has a lot of electrons on it, and you put it in a electromagnetic field, you can actually shake the electrons off of it, and this actually creates a charge. So it basically reacts to charge, and then using a positive and negative grid, you could attract these ions, these xenon has few less electrons, and then accelerate it out of the craft. So the xenon atoms are heavy, and this creates momentum. So actually, enough of these little guys being shot out of the spaceship creates enough momentum for this thing to propel your craft. It creates that cool blue light that you see in a lot of photos, the blue glow, that's xenon ions. And they use a lot of ceramics. The electron gun assembly uses ceramics here in terms of distributing, bringing the electrons in. It uses high temperature. Thermal process that heats up a tungsten carbide or tungsten material so that it sheds electrons. Of course, that has to be held by ceramics. This whole thing could be at 10, 20,000 volts. So we have to have ceramic insulators to allow us to do that. Inside this thing with these magnets, we have this gas that the xenon is being stripped of its electrons so that can be shot out. So that uses this negative and positive grid. These are completely electric devices. They have a gas storage that actually provides the xenon, and there's other gases you could use that are in there. There's some solid gases that they're looking at you bringing in now, sublimating gases. So this actually creates this ion engine. So they're really simple component, no moving parts. Ion engine has no moving parts. It's reliable because there's no moving parts. It needs reliable insulators, a reliable containment system, lightweight. But again, it's just a perfect vehicle. And the question to you is, how fast do you think an ion engine can go? That's a good question. NASA DART, or if you folks, is there really a top speed to the ion engine? That's more of the other question. Ion propulsion system roles. Here's a little kind of idea of the distance we could go with ion engines. If you're close to the planet Earth, you could use solar panels, and that allows you to get around, so you can energize, you can use solar energy and a battery to create the electricity, to make the propulsion system work. Once you get to the asteroid belt, it gets pretty tough in terms of solar power. You don't have enough sunlight. So you need to have a different energy source. So the ceramics are key here, that you have some sort of nuclear energy source, like a 100 kilowatt reactor, so that you can actually have the energy when you go out there. So again, nuclear energy, and there's a lot of borides, boron carbides, or borons used. Boron is actually a neutron absorber, which is B4C, and that's used a lot with alumina and dielectrics to help manage the reaction rates in nuclear reactors. So it's a great boron application. And as you go out to the really far distances, which you're out, again, near Neptune, you then have to go for some more solid state, like definitely a radiation source that could be a isotope radiation source. So these are things that are going to make it difficult for human travel. Radiation protecting for the people in the craft is, and I'm working with a company called Melogen Labs right now, which is looking at creating lightweight radiation absorbing or proton absorbing materials is required. So when you go out into these distances here, you're talking about having radioactive sources, and you need to shield yourself from radiation, not only from space radiation, but from the power source itself. Another things about deep space ion engine, this is get you think, I'm using solid iodine instead of xenon, and I want to actually vaporize it. Some people could do this to create the gas for the ion engine. Iodine is pretty massive. It has a good momentum when you accelerate it. But what are the operating conditions in space? And this is what Fralock, we really work with. Minus 269C to 600C. You can have a big range in operating temperatures. You're in vacuum. It's 10 to the minus 9 torr. So outgassing is a problem. You have any lamination things, bubbles can form that could create problems. When you're launching, you have high gravitational forces, G's, that shake things. So you got to be able to withstand that. So your design has to be robust in that way. You can't have things outgassing. And then there's the reliability. You have to turn the engine on and off to make it thrust or position itself. It could be 100 milliseconds to 30 seconds to, in some cases, hundreds of years. So depending on where you're going with your ion engine, your system has to be reliable. And there's a lot of materials. In this diagram on the right shows you kind of some of the technologies Fralock provides. Flexible control cables, heater systems, thermally insulating materials, or they could be thermally conductive materials, and then the vessel itself that actually would provide the gas to feed your ion engine. So again, you can kind of see all these things that are required. Now Fralock consists of different teams. So all projects, and you'll find when you get into industry or even in university, are team-oriented. It's not just you. As a material scientist or as a mechanical engineer, you work with a team of experts to provide a solution. So even at Fralock, we have different material scientist experts that help us solve problems. And this is how we arrange. We have specially engineered materials, engineered technical ceramics, that's my guys, advanced flexible interconnects, and then we work together to get you a solution. So a little bit on my team and kind of how we help with space vehicles is we make ceramic components. We make ceramic circuits out of aluminum nitride. We make things out of aluminum oxide components, and we do all these capabilities. So this is old school stuff, like a machine shop. We do sinter the material. We process it in soft before firing it, so we get the shape right. We fire it kind of like the old days they did 20,000 years ago at some sort of kiln. And then we help with designs and also with working with our customers, so we could get the right shape and the right material properties, so that it creates a reliable application for them. So this is a little bit some of their general products. We make, especially for our ceramics division, is aluminum nitride ceramic heaters. These are really thin, like the size of a credit card, or it could be a very small cell phone, and they're capable of heating at rates of up to 300 degrees C per second. They're very reliable, and they use a combination of tungsten metals and aluminum nitride. Aluminum nitride is a high thermal conductivity ceramic. Its thermal conductivity is similar to copper metal, but it's a dielectric, and it can be made thin, and it's rigid, and it's actually pretty lightweight with 3 grams per cubic centimeter. So it is very good for space applications, deployable, and also works well in a vacuum. So here's an example of one of our heaters. Our heaters themselves are created with multi-layer technology. So The ceramics are layered one by one layer of aluminum nitride tapes that are then put together. We can also put channels in them to allow for heat dissipation. And this creates a very compact heater that we have multiple zones. So using our lamination technology, we can have easily 50 thermal zones, including embedded thermal measurement devices like we call RTDs. So we have feedback, so then we can actually watch what's going on. So here's an example of heating of one of our heaters, a multi-zone heater, showing how it increases temperature as we fire the different zones. We can change the thermal profile. Really amazing use of aluminum nitride and tungsten. They have the same thermal expansion properties, so this thing doesn't warp when it heats up. It stays nice and flat. Uniformities can be within a degree C over that entire surface in terms of thermal uniformity. All right. I'll move on to our other team, specially engineered materials. Thermal interface materials. In space, there's no convection. Heat transfer is basically either conduction or radiation. And you'll learn this in school, or you may know of this. So if you have two things that you want to heat, so if you want to apply heat to something, you need to smash something in between that device, your heater, and what you want to heat. And these are thermal interface materials. And graphite is a famous material. And what you do is you use them as a sandwich, and then the more force that you can provide to push the things together, the better your conduction heat is. So when it comes to outer space, any air gaps are bad. So you want to fill that in with a material that actually has thermal conductivity. So these are called thermal interface materials. Other people may see them as gaskets, but it's a good thing to keep in mind if you're ever designing a heater and you want to provide reliable heating, that you have to use a thermal interface material. They're considered a crucial part of thermal energy systems, and they'd be customized for use in space. So here's kind of how we characterize them. It shows you how they're used. We're looking at thermal resistance. We have a system where we have a heater and a cold plate. We put our sample in there, and then we're using this ASTM. We actually crush them. So this is together, and then we increase pressure, and then we actually then measure the amount of heat moving through the part. It's kind of some pictures of what it looks like here. You can see it. Again, what we're looking really is the contact interface. So smooth surfaces are good in terms of their ability, but if they are rough, the thermal interface kind of gets squished in between them. It helps thermal conductivity. And then what you see then is that you're in this lower corner is that bulk thermal conductivity is actually improves as you smash things together, higher pressures in general. And then different types of materials do provide different levels of thermal conduction. So when you're working with your ceramic heater, you want to heat up that ion engine, that vessel, you want to talk to your engineers to make sure you select the right thermal interface material that doesn't outgas for your space application, so you can reliably transmit heat into the device to get it to work as you want. So again, there's a lot of different products. This is just a quick showing the kind of the multiple products we have, some that are in the different environments that we test in. And this is the catalog stuff, so you can see it on our website. But let you know that in general, I would seek experts to work with experts to help you navigate the system of these materials. And I worked with a Dr. Simin Mokhtar at Fralock. She's phenomenal in her ability of helping you with these materials. Flexible interconnect products, when you need wiring in space, you could do that by taking copper and you clad it to a plastic, and then you could etch it, and then it creates very flexible circuits. They're acrylic, they could be polyimide, they last up to maybe 200, 300 centigrade. These are from our Chatsworth and Milpitas companies. And they're really flexible service that allows you to make connections. What's nice about them is they could go to minus 269 centigrade. So now you have something that makes an electrical connection in your spacecraft, and also very robust in terms of vibration and shaking. They could be very flexible in shape and work with your design team, and then you could do some plating on it. And they're very flexible, very reliable, and able to travel well in space. Here's another example of kind of an application between two components, folding out like a folding solar panel array in space. You can see the use of these flexible electronics, robust, they can fold. You don't have solder joints. You have fine line spacing, so you could have a lot of information or like power flow, super lightweight, and exceptional radiation resistance, because remember, in space, there's no atmosphere, there's nothing protecting you, so you have to withstand radiation. And then again, you have to be able to not outgas. So we have laminate, adhesive-free technology that we developed at Fralock, so we can make these connectors without having any glue, which can make bubbles. Again, kind of a summary. From Fralock, utilizing a range of engineered materials and advanced manufacturing processes, we deliver high reliability solutions to meet our customers' unique application requirements. And we're a premier partner for critical aerospace applications, distinguished by our unwavering commitment to our customers, suppliers, partners, and employees. And then kind of overall, to wrap up the talk, ceramic materials, as we've seen, have been around for over 30,000 years, and they've really been impacting our lives the whole time. Ceramic applications continue to grow. They help us live better, make us healthy, help us with energy, help keep us safe, and it can make commercial space exploration a reality. Reliable space travel really requires clever engineering, teamwork, repeated testing, and using the right special materials when required. So you're a team. Remember, it's not up to you to respond to fix it yourself. You can engage people that know what they're doing and work together. And then for everybody, participating in Explore the Space is fun and will help you learn. A small donation to ETC helps us continue our mission, because we are a nonprofit to educate young minds. And I've been doing this, I think, for 5 years with DV. The online courses are technically intensive, and they're not basic stuff. They're pretty severe. I've helped DV develop the online courses, and these webinars feature experts from industry and potential connections, so other value to explore the space. All right. I don't know if DV has any questions or.
Thank you. Thank you so much, Tim. That was, as usual, very inspiring and very encouraging for our mission on space education. What we intend to do is to put your questions in the chat box and also send the email to the participants, and then encourage them to answer them, so that that gives them an opportunity to stay connected. With that, I thank Mr. Tim Dyer on behalf of all of us here for this wonderful presentation. Thank you so much, Tim. Thank you for thank you for that great presentation. Ladies and gentlemen, I take pleasure in requesting and welcoming Dr. Manisha Vidyavathy, HOD, Anna University on the Department of Ceramic Technology, for her presentation. Madam Manisha Vidyavathy graduated in physics from the University of Madras. She holds a post-graduation degree in material science and ceramic technology from Anna University. She obtained her PhD in ceramic technology from Anna University. Thank you, Dr. Manisha, for being with us. Over to you, Dr. Manisha.
Good evening and good morning to the people from the international. It's a very great pleasure for me to talk on the exploring the career opportunities for a ceramic technologist and aerospace sector. So I thought I would focus on aerospace sectors, because it is exploring the space. So I thank Sir for giving me this opportunity, and also my mentor, Dr. L.K. Sharma, for giving me this opportunity. So before I go into the exploring the career opportunities, is my slide open? You're able to see my slides?
Yes, we can see it.
Yeah. So why ceramics has been used in, I thought I would give a, since there's a lot of student community in this webinar, so I thought I would give a small intro about why the ceramics is used in aerospace applications, and then go into what are the possible opportunities that is available for ceramics. So the advantages of why ceramics is used in aerospace applications is it has got a high temperature capability. It can withstand very extreme temperatures. It has got very low density. It reduces the overall weight by improving the fuel efficiency and capacity. And it has got an protects against oxidative and erosive environments. But the challenges that is being faced by using ceramics are brittle in nature, and they have very it has to be manufactured with complex fabrication techniques and joining and rejoining. So some of the common materials that are being used for these aerospace applications are the oxide ceramics, the non-oxide ceramics, and composite ceramics. And the future is on the ultra high temperature ceramics, self-healing ceramics, and on the fabrication, it is the 3D printing. So where are these ceramic materials probably used in the aerospace applications are first is on where space shuttle thermal protection systems, where they are used as a heat shield to protect the shuttle during atmospheric re-entry. And the key materials where they use are in the RCC and as well as the silica tiles they use in the space shuttle technologies. And the challenge that is there, that is being faced in this particular development, is the vulnerability to damage from debris during the launch. And the second application where ceramics is being used is on jet engine turbine blades, and where they give coatings on nickel-based super alloys in turbine blades for high temperature resistance. And stabilized zirconia offers low thermal conductivity and resistance to thermal shock. But again, the challenge here is durability of the TBCs in harsh oxidative and erosive environments. The third area where they use is on the hypersonic vehicles, probably the nose cones and hypersonic edges of the hypersonic vehicles that face very high temperatures. The key features here are they have high melting points and superior resistance to oxidation. So the challenge here is to balance the thermal conductivity and strength. The fourth area where they use ceramic is on the rocket nozzles. And here the materials have to withstand very high thermal and mechanical loads and ablative properties to ensure controlled erosion under extreme heat. But again, the challenges here is expensive manufacturing processes and fragility during handling. The next area where they use is on the missile dooms, where the applications are on the infrared windows and sensor covers for guided missiles. And the key features of the material should be they should be highly transparent to IR radiation, and they should also have superior hardness for protection. So the challenges here is precise machining and polishing for optical clarity and its a limited scalability. So the potential career opportunities in as far as ceramics is concerned is first on the engineering and design. So here the role can be as an aerospace engineer design to develop and design and test aircraft, spacecraft, missiles and satellites, or as a structural engineer to focus on the structural integrity of aerospace vehicles, or on the avionic as an avionics engineer where they'll specialize in electronic systems, or as a material engineer to develop advanced materials like composites, alloys, and ceramics for aerospace applications. The second career opportunity is on manufacturing and production. So, as a manufacturing engineer, to optimize the production processes for aerospace parts and systems, or as a quality assurance specialist to ensure products meet stringent aerospace standards, or as a tooling specialist to design and create tools for assembling aerospace systems. The third career opportunity is on the research and development, where there are many sectors where students can work on these aerospace applications. The first is on the advanced material development to develop high temperature ceramics for engine components or thermal protection systems or spacecraft heat shields, or work on the carbon matrix composites that are being used in jet engines and hypersonic vehicles, or design ceramic materials for aerospace applications which require resistance to extreme environments. The other area where they can work is on the thermal and structural applications, where they can develop ceramics for insulating spacecrafts and protecting them from re-entry, or design a lightweight, high-strength ceramic components for satellites, drones, or aircrafts. The third area where is on the R&D activities where they can innovate ceramic materials for next generation technologies or materials for vehicles that operate at extreme speeds and temperatures. And the next area where they can work is on manufacturing and quality control, where they can develop processes for fabrication as well as ensure components to the aerospace standards. And the other last area where they can work is on testing and analysis, like the failure analysis or thermal and mechanical testing. So the future of aerospace innovation depends. So as a ceramic technologist, they can refine materials and processes so that we can have a new era of efficiency, safety, and sustainability in the aerospace industries. So some of the organizations and industries which work are on aerospace companies like Boeing, Airbus, Lockheed Martin, SpaceX, and Blue Origin, and research institutions are NASA, ISRO, DRDO, and ESA. And ceramic material manufacturing companies are Crookstech, Kayora, and Saint-Gobain. So thank you.
Thank you very much, Dr. Manisha. Thank you for
So
that. Yes, ma'am.
So
Yes,
I
please.
didn't focus on any other applications of career opportunities. The career opportunities specific to aerospace applications.
Thank you, ma'am. Thank you so much. We are very keen to work with your department and your students. It will be our pleasure to take this forward. Ladies and gentlemen, I thought it will be good to request Dr. Subhash Rasbut, who is present with us here, to say a few words on what is happening in the Indo-US spectrum, particularly with relation to the space industry. May I request a few words from Dr. Subhash Rasbut, please?
You're on mute, Subhash. Sorry.
Dr.
Okay,
Yeah.
can you hear me now? Yeah, I was muted. So
Thank you.
Yeah.
Okay.
Yes, please.
all right. Well, I really enjoyed hearing everything. I mean, Tim's talk was so comprehensive, including the Fralock business here in our area, also San Diego, and the breadth of it is astonishing. I mean, I've been educated tremendously with all the slides I saw in Tim's talk, and also the talk that Dr. Anusha just gave. Manisha just gave. One question I had was in terms of the student projects, and Tim and I have a plan to discuss this also. Is there a possibility of a student who is taking on a PhD project, say this fall, to take on any of these topics, or is that too sciencey and not enough technology? I mean, because we need to have a master's student, we have quite a few of them that are ready to do more or less all the things that I just heard Tim and Manisha talk about, including stuff on aerogel, carbon composites, non-oxide ceramics, high temperature, all of that. The difficulty we have is finding the right match that will be more applicable, and it's coming out of the brain of Tim and Manisha rather than professors who are more used to thinking in terms of, oh, where are we going to publish this? But that's not the mindset I'm sure industry wants. So how should we approach this dilemma of the project? For example, a master's student, she was just in my office yesterday. She wanted to work on carbon composites. And I didn't have an immediate idea for her, but I said, okay, I'll talk to all my contacts like, Tim and all of you here in Manisha, that what exactly should the focus of that be rather than, well, put it under a transmission electron microscope and get a high resolution image of atom by atom by atom. But that's my sciencey thought. What should be the technology end of a master's thesis like that, Tim or Manisha?
Like when we select projects for our collaborative work with UC Davis, we look for projects that are technically challenging but commercially significant for us as a company. But we also have the same matchmaking challenge as we like to find the right students that will work with the project. We currently have a student from UC Davis, Raven Batista, who's working for me in Poway on a project using characterization of biomedical aluminum oxide materials. And she's doing this on a 3-month project. So our vehicle is, we bring her in for 3 months on this project. And she did complete her bachelor's degree at UC Davis. So we look at her, but she doesn't know what her future is. And it's okay out there, everybody. If you don't know when you get out of school what you want to do, that's pretty normal because there's a lot of options. So for us, this is an important, we have a biomedical customer that uses a device that's used in gene sequencing. So we're trying to support gene sequencing. So it's a biomedical alumina project. So we select that. We have our heaters. We're doing work with silicon carbide. We do a lot of work with silicon carbide processing. So from industry perspective, we look for people that have the technical background and kind of the practical knowledge to help us. But these projects, it'd be nice to have a larger project. So my vision would be having projects, because material science projects don't end in 3 months. And a PhD project is a much better way of doing it, because you can make a more significant impact, because material science is like peeling the onion. And so I think it takes collaboration with academia and universities to kind of find these projects. I'm interested in what Dr. Manisha, if from her, because I'm US based and I'm UC Davis, and Manisha, do you have any what do you think on collaboration for solving problems?
I think that, yes, please. Yes, Dr. Manisha.
Yes, sir. Yes, sir. You finish, sir. You finish.
I thought that the Indian Ceramic Society, of which Dr. Manisha is a key person, and also Dr. Sharma ji, can play a very important role in this. Over to you, Dr. Manisha. Dr. Manisha.
Sir, as far as our university is concerned, we mostly make the students to work on material development. So they know for what application they are working on. So they know the properties of that particular material, and we try to tune them to develop materials for that particular application. So we don't spend on the processing and so on. We try to develop materials. So we make the students to develop materials. So,
but when you say that, Dr. Manisha, you mean to say the composition of the material or the method by which it is made?
the composition. So, for example, sir, we have a 3D printer. And what the students do is that we have a 3D printer, where a resin 3D printer, where the resin is given by the company. And from this, what they do is they have the material given by the company, say, for example, is an alumina or thing. And they start to do it. They give that composition, they give the fixed composition, the resin, everything, and they do the printing. But our students, they literally focus on developing a material, and for that material, they develop the resin.
I see.
Be 3D printed.
I got it. Yeah, thank you. Yeah. So yeah, I mean that introduces a lot of breadth. When you say developing a material, that means now you're basically looking at a periodic table essentially, and then within the ceramic range, that is. I mean, as Tim was saying, if you're thinking of boride carbides, or oxycarbides, oxynitride, or glasses made from it, or glass ceramics made from it, there's a range of such materials development abilities. So yeah, so no, that is the right direction to take, certainly. And but good. So will those be, Dr. Manisha, master's theses, or?
No, sir, we do it at the undergraduate level. At the undergraduate level itself, they do.
Okay, got it. Yeah. Okay, well, that's very promising. So, DV, I'm so glad to hear that this collaboration is continuing, and we'd love to see our department and my group particularly, proceed with that. I'll talk to Tim separately about, since we are kind of within walking distance of each other, so to speak.
Almost, yeah.
More or less. On a good day on the freeway, yes. But,
yeah, maybe 45 minutes. Yeah, but it's and the campus is great, and just I want to add a little bit about. There are things in industry we don't have that the university have. We can't operate it by ourselves. So a smart company works with universities or collaborates. An example is a Professor Yayoi Takamura at UC Davis has the best I've ever seen X-ray diffractometers. She has 2 Rigaku, one that operates at high temperatures. So Fralock, we see this as a valuable thing that we can actually run experiments at 1500 or 1600 degrees centigrade, so we can look at material structures as they're being sintered. There's also they have a lot of capabilities to do tests that we just don't have the resources for, plus the expertise. So Dr. Takamura is great with magnetic material characterization, but also she has this piece of equipment which we can use on recharge basis, which we don't have to buy, and then our material scientists learn too. And we all keep learning, and that's why I'm involved with Explore the Space and also with UC Davis as an advisor to the College of Engineering and Material Science, is that we always going to keep learning. So everybody should understand that learning never stops when you leave college. University, you always got to keep learning. And really, as industry, you cannot keep called not invented here syndrome. We don't want to suffer from us inventing everything. We want to work with experts who have also invented the solutions, so then we can combine them to create a product or a reliable vehicle that uses the contributions of others. So to never just pay attention to what's in your hands, to also look up and contact the people or in expertise. And universities definitely have a clear role in industry in collaboration. It's just, we can't do this by ourselves.
If I can add a couple of sentences to that, Tim is exactly right. Our facilities like the X-ray, but on the synthesis and processing end of it, the spark plasma sintering machine we have for years and years, ever since Kazuya Yamazaki and I started that in the early 90s, Tim might remember, is a very underutilized facility. Even people on the campus don't use it often enough. The SPS, it's called, previously called plasma activated sintering, now SPS. It's a great machine. It can go up to high temperatures, like well over 2000 in many cases. But we don't have utilization of that to the extent that we would want. So, I'm certainly going to talk to Tim about it, but any of you others from India or elsewhere want to send us some powder samples they would like to do in addition to 3D printing that Dr. Manisha was saying by SPS machines, unless they are widely available at Anna University, I don't know, but SPS is a fairly interesting technique of getting rapidly densified things from powder to disk in a matter of minutes without any green processing at all. So you don't do slip casting, none of that. You go from powder to disk, as Tim well knows. But again, chemistry people come and use our SPS machine, but the engineers don't want to look at it. So I would like to sort of put the flag up there for our little magic machine sitting here.
Dr. Subhash, we would also like to make use of this opportunity to welcome students of UC Davis to consider coming to India on a study tour. We have been discussing this.
Yes.
Explore the Space along with its partner organizations. We'll be more than happy to connect the students of UC Davis to opportunities in India. We look forward for that. I've been discussing with Tim to put together a study tour on space technology for entrepreneurs and students to the Silicon Valley. And it was very nice of Tim to have connected me to Mr. Amir Saidi. And I'm talking to Amir Saidi of UC Davis on this. So I think we'll be doing tremendous good to students on both sides, both India and United States of America, if we can exchange this student exchange. And we look forward to working with you on that, Dr. Subhash.
Yes, I agree, and I totally, be on the lookout and be in contact with you and Amir as well, because he's the successor of my senior design course. And so absolutely great idea, Devi, and we'll certainly keep that in mind very much.
Students, are there any questions? We have put the questions based on Tim's presentation in the chat box. These questions would also be reaching the individual students who are participating in today's webinar. We encourage you to answer these. That will give you an opportunity to stay connected. Any questions from any one of you?
I have a question to Subhash sir. Sir, do you have any exchange programs for the students at the undergraduate level in your universities?
There are, but they are again under the auspices of things like the Fulbright program or that program or this program, but it's all across the campus. So I've been trying very hard, because since I was the director of our Internship and Career Center for 9 years on this campus, to go through the Internship and Career Center to create these opportunities. And there it's a bigger program, because the ICC, the Internship and Career Center, places 6,000 interns worldwide every year. And that goes from Mexico to Italy to Europe, but very few to India, because I think that's where we need to push interns who are interested in physics, chemistry, geology, social sciences, to try taking, like, DV was suggesting, and you are too, that can you go to India and spend a summer there working on a research project? If you're a physicist or a chemist or a biologist or a geologist, and that's what I've been trying to push because of my ICC connection. And that was the place, Dr. Manisha, where we should start. So
Yes,
if you such possibilities, we could certainly explore those. And I can identify undergraduate students who would want that.
yeah.
We plan to talk to the Physical Research Laboratory, PRL. It is headed by a gentleman called Mr. Anil Bharadwaj. Mr. Anil Bharadwaj is a space scientist. He's a very famous space scientist. We have had the opportunity of interacting with Mr. Anil Bharadwaj. He heads the PRL, which is based in Ahmedabad. PRL was founded by Mr. Vikram Sarabhai, the father of the Indian space industry. So, Tim, we plan to invite Mr. Anil Bharadwaj to one of our forthcoming sessions. So
Great.
that's going to add more value to what we do. On that note, may I request last words from Tim, please? Over to you, Tim.
Again, it's just, I don't want to be repeating myself, but really, Explorer Space is something that's been a project. DV and I met during COVID, the time, or I think maybe it was even before COVID, on the idea of how do we promote or folks getting into technology and engineering education, and also then working in that field. How do we help people do that? How do we inspire young students to do that, or younger people? Space inspires us all. We all had dreams about space. My father taught me about space when I was a young man, and I had a telescope, and I would look out. So space is something that brings us together. We all are fascinated by it. So Explore to Space, that's why it exists. Is we want people to reach out. It's a great way that we can internationally work as a team or collaborate. So the webinars are part of that, and DV gets awesome speakers. It's amazing. It's who he gets is tremendous. So it's an exciting event. The speakers are very good, and you'll learn a lot. And also there's an online class that you can take. Again, you could explore with DV's website, Explore to Space, so you find that, because that's something that DV and I put together when I was at Elcon. And again, it's very, very, very good program. So I suggest folks to be involved. And also remember, it's a charity institute. So if you, any little donation here and there helps us out. And we hope in the future to have a friend of mine from Israel, very inspirational woman, strong woman business person. But because of, we pray for Israel right now, but certain things she couldn't, she has to worry about her family. She couldn't make this event. So hopefully we could have her later on, Orly Shea, to come speak with us, because again, that really helps. So we like to have a good range of speakers. And again, Explore the Space is a real great opportunity for you folks to meet other folks. I mean, it's in connections is what you get from the webinars.
Thank you.
Thanks,
Thank
DV.
you so much, Tim. Thank you. Dr. Manisha, a last word from you, please. Dr. Manisha, please.
Yes, sir. Really, this is the first time, and it is a good initiative. And as per discussion, we would try to include one lecture, one course, a credit course for our in our curriculum.
Sure, man. That's a great encouragement. We look forward to working with you. Our special thanks to Dr. Subhash Risboot, Dr. L.K. Sharma ji, and Dr. Subbarao Pavluri, with whom we intend to work further. Special thanks to all of you. Special thanks to all the students who joined here. Thank you again, Tim, for being part of this. We look forward to be in touch with all of you, and very soon you will hear about the second edition of this webinar series. Thank you so much. Good morning again to United States of America, and good evening to friends in India. Thank you.
Thank
you.
you,
Goodbye.
Thank you for organizing it. It was a great time.
Thank you.
Thank you, madam. Thank you.
Thank you.
Thank you, sir. Have a good
Thank
day.
I'll see you in Daytona
day.
Beach. Yeah.
Thank you.
Thank you.
Okay.